Hello. Today we're going to talk about force vectors, and we're going to split this up into two parts. We actually did this PowerPoint back in the fall semester, so hopefully all this seems very, very familiar to you, but we just wanted to go through it one more time because we are going to be using a lot of these concepts as we go into our bridge trusses, which we're going to start looking at here pretty soon. So one of the things that we talked about quite a bit in the previous section or previous semester was vectors, and we just had a video about vectors not too long ago. But just want a quick reminder again what a vector is. So we talk about vectors. They do have two parts to them. We have a magnitude and a direction. And so that magnitude is the amount of whatever it is. So whether it be force or speed or velocity that we're talking about, or if we're talking acceleration. But the amount, the number part of that is your magnitude. And then the direction is just which way is it going. And so we could label that like northeast, southwest. We could talk about it in terms of angles. A lot of different ways we could talk about direction. Typically, we're going to be looking at it as an angle, and we'll have to think about, which angle are we talking about in reference to which reference point or which reference line. And so we'll look at that a little bit more as well. And then vector notation, we talked about this also in the fall, but when you see a vector, generally they're going to be written with an arrow over the top. That's just kind of a way to designate that versus maybe just a side length or something like that. Sometimes in a book or something like that, they may use just italicized, capitalized, bold type of lettering for a vector, but generally the more accepted way to do that is to use the arrow over the top of the letter. All right, so when we look at this is a good example of what a vector might look like. So here we have the arrow that represents our vector, and the length of that arrow is going to represent its magnitude. Now they're trying to say it's 3 units long, so they're dividing it up into 3 units. Generally speaking, we try to be very good about scaling the length of the vector to whatever size that we're doing, because you can definitely do vectors geometrically. You can draw them all out. And then connect them head to tail and do some math that way. But we find that generally speaking, drawing them out is a little bit tedious. It's hard to do a good job of. It's hard to be accurate as much as we'd like to be. So while we can definitely do everything geometrically and draw them out to scale, generally we don't worry about that too much. We usually just approach it mathematically. So anyway, the magnitude is the length. In this case, they're saying it's 3 units. And then the other part we want to talk about is the direction. And so the direction is really this angle that we're looking at. We do have to know kind of what our reference is. So here they're referencing it against the positive x-axis. That's how we're measuring. We're measuring counterclockwise from that positive x-axis. But there's a lot of different ways you can do that. You can use cardinal directions, north, south, east, and west. You can use it with an angle. So you might see somebody say, you're 30 degrees north of east. That would work as well. Or you might measure it from the positive y-axis, or a lot of different ways you can do it. The main thing is just to be clear. Make sure that what you're saying is clear to whoever it is that's reading and looking at your thing. Now, obviously, a picture is a way easier way to go. If I draw this picture out, it's pretty obvious what I'm talking about. So you can get by with just trying a good picture. But if you're trying to describe it verbally or write it out, longhand, in a sentence structured format, you want to make sure that you're using proper descriptive terms. So again, this one they're going to say is 30 degrees counterclockwise from the positive x-axis, and that is a good description of it. But again, the picture is going to be probably a easier and better way to show that. And then we talked about this earlier in the year too, the sense of it. And again, sense is not a big deal. It's just kind of you using some intuition and common sense to say, which direction is this thing going? So in this case, it is going up and to the right. So that's what the sense of it is up and to the right. But it is important to kind of understand, like, which way do we think this thing's going? Because that's going to tell us something about the positive or negative sign of our components, or x and y components. Is it going to be a positive x value, or is it a negative x value? Is it a positive y value or negative? And just like we see in math, up is positive, down is negative, right is positive, left is negative when we start looking at these values. And so here's just kind of a quick chart. Again, we did all this PowerPoint before. So again, right positive, up is positive, left is negative, down is negative. So just remember that. And so when we start drawing things out, and we start drawing out our vectors, if it's going down, then your y value should be negative. If it's going left, your x value should be negative. If it's going right, your x is positive. If it's going up, your y is positive. So again, not a big deal, but just something to be thinking about as you're doing the problems. Don't forget and don't make a mistake on that. Quick trig review. We already know most of this stuff, but just going to remind you, we are dealing with right triangles when we draw this stuff out. Not to say that everything will be a right triangle, but we're going to form right triangles as we do this. And generally when we do that, our hypotenuse is our vector. And then we're going to draw the two legs to represent the x and y components of that vector. And so that's how we're forming that right triangle. And so things that we know that the right triangle that we form with our two legs is going to be a 90-degree angle. That means the other two angles have to add up to 90 because the sum of all those angles have to be 180. And so if they give you one angle, like this one down here, we should be able to tell what this angle is because we know that these two have to add to 90. So you may not be given all three angles. Very rarely are you going to be given all three, but you should know all three if you do just a little bit of work. The other thing you're going to use occasionally is Pythagorean theorem, and we're going to use that when we're trying to find either the length of the hypotenuse given the two sides, or maybe we know one side and another side, and we're trying to find the third. But if we know two sides of a right triangle, we can always find the third using Pythagorean theorem. And that is something we're going to use. Again, for us, primarily, we're going to use it when we're trying to find the length of a hypotenuse, find the length of that vector, if we know the two sides. That's the most likely case for where we're going to use that. And of course, the trig function, sine, cosine, and tangent. And we had a whole video on that, so hopefully you already watched that. If you haven't, you should go review that just to make sure you remember how to do it. But we'll use sine, cosine, tangent. Just a quick reminder, everything is in reference to the angle. We shortcut on all this stuff because it's easier to write it this way. But this is opposite of the angle theta. This is the hypotenuse, which that won't change. And this is adjacent to the angle theta. So when we say it's the opposite side or the adjacent side, that is opposite and adjacent from the angle we're looking at. So if I were looking at this other angle up in the top, then my opposite side is this bottom, and my adjacent side would be over here. So you just have to make sure you're paying attention to which angle we're talking about. And again, most of the time we draw this picture this way because that's how it's probably going to work out. But there are occasionally some places where the angle we need is actually the other one. And so you just have to make sure that when you say opposite and adjacent, you're thinking opposite to the angle we're looking at and adjacent to the angle we're looking at. So here's a quick run through of how that looks like, or how we're going to use this. So in this case, this side f of x, our adjacent side, is our x component, the x side of that, and the opposite side is the y side. And that's, again, most of the time that's how it's going to work out. Not every time, but most of the time that's how it's going to work out. And our hypotenuse then will be just our force. So x and y components are the two legs of the right triangle. Hypotenuse will be our actual vector, our actual force that we're looking at. And so to find f of x and f of y, we're going to use sine and cosine. Again, we're going to use sine to find f of y in this case because sine deals with the opposite and the hypotenuse. And so the opposite side is fy, hypotenuse is f, so we're going to use sine for that one. To find f of x, we're going to use cosine because that side is the adjacent side to my angle. That's why we're picking that, because we're looking at the one that involves the side we're looking for and the side we know. And so you would solve those. The only time we really use tangent in anything we're doing, tangent does work, obviously, is the opposite over adjacent, so it's fy over fx. Generally, the only time we use that is if we're working to find this angle. So if we know these two side lengths and we want to know what is this angle right here, we can go ahead and use tangent to find that. We'll do f of y divided by f of x, get that value, and then we know that the tangent of that angle equals that value. And so we're trying to solve for the angle. So what we'll end up doing is do the inverse tangent, and we'll just do it on the calculator. So we'll do inverse tangent of fy over fx and solve that value to find the angle. But this is stuff we looked at before. So to find fy, it's just going to be f times sine theta if that is our angle. And f of x is going to be f times cosine theta, again, if that's the angle. And when we start drawing these out, we do have to pay attention to which way is it going. So again, in this case, our sense is to the right and up. So it means both of these are positive values. But if we went left or we went down, we'd have to make sure we're making these negative. That really won't affect the triangle itself, because of course, obviously from geometry, we know that the lengths of the sides of a triangle are always positive because you can't have a negative length. But when we put the negative in front of it, we're really indicating direction, not the length of it, but the direction of it. So when we say it's negative, that won't affect anything that's happening as far as finding the length of the hypotenuse or anything like that. It's just telling us which way is it going. All right, so we just want to look at some examples of how this is going to work. So we're going to split this up into two parts. So this first part is going to just go through the basics, and then we'll do it in a separate example in the second video. So if I have this vector that's 75 pounds, it's got a 35 degree counterclockwise from the positive x-axis. So you can see that picture right there. It's going to the right and up. What we want to do is we want to find the x and y components of this vector. And so we said, okay, well, since the x side is the adjacent side to this angle, that is going to be the one we use cosine on. The opposite side, go ahead and draw this in here. The opposite side is the y side, so that's the one we're going to use the sine value for, because sine is opposite over hypotenuse. So we're going to find those two values using sine and cosine with this angle 35 degrees and the hypotenuse, which is 75 pounds. So let's take a look at how that looks. All right, so for this first one, again, we're using cosine. We know our angle is 35 degrees. We know f of ax, that is our x component of a that we're looking for. And then 75, that is our hypotenuse. So we're just going through here. So we're going to end up with f times cosine of the angle. And they've kind of walked you through all the steps to get there algebraically. But our shortcut straight to that formula is f times cosine of the angle. And again, they're putting up here just to remind us which way it's going, because it's going to be positive. So you're going to do 75 times cosine of 35 degrees. And this is, again, something you're going to put in your calculator. There are some trig values that you should probably know once you go through trig. But for right now, I'm just going to use the calculator. Plug in the calculator. Just make sure we're in degree mode. There's different modes that you can be in on your calculator. So you want to make sure that your calculator's in degree mode when you do this. Otherwise, you're going to get an answer, but it's going to be the wrong one. The other mode that you're likely to be in would be radians. Just depends on what kind of calculator you have, if it defaults to degrees or radians. But when you get into trig and calc, you use radians quite a bit. And so there is a possibility that your calculator may default into radian mode. And we're just going to multiply those two values together. And so in this case, we get 61.4 pounds, which is telling us basically how much of this 75-pound force are we pushing in the positive x direction with. So how much that force is going that way, how much force are we pushing our object that direction with. And then we'll do the same thing for y. And so again, we can go through the whole step here, but we'll probably shortcut out of that and say that it's opposite of hypotenuse. Here's the algebra. But again, it comes down to, once you solve that, it is the force times the sine of the angle if it is the opposite side, which it is in this case. And so we'll multiply those again, and we'll see we get 43 pounds. And since our angle is less than 45 degrees, that makes sense. The opposite side should be shorter than the adjacent side. So that's a quick check for you. If you're getting an angle that is less than 45, you should get a smaller value for this opposite side than you do for the adjacent. And that, if you're not, then we need to stop and take a look at what we're doing. 45 degrees is where those two should be equal. And then if we get above 45 degrees, then it switches and opposite should be the longer side. All right. And so vector B, this is just kind of looking at what happens if we are actually going in a negative direction. So here we're going to the right, but we're going down with our y. And so since y is going down, that means once we do our problem here, y should be negative. Again, it won't affect anything about lengths to the sides or anything like that. It's just going to be, when we write that value out, because it is going down, it needs to be negative. And these are all the same values as the last time. So we do x, it's the adjacent side to this angle. It's the side next to it. That's what adjacent means. And then y is our opposite side. So we'll find the x, same way we did last time. It's going to be the hypotenuse, the vector length, times the cosine of the angle, because we're looking for this adjacent side, so we're using cosine. So we take cosine of that angle. And so we should get the same value we did last time, which was 61.4. And that's positive because we're going to the right. And then to find the y value, again, same thing we did last time. It's 75 times sine of 35. However, now we're going down. So that means once we get this value, we're going to make it negative. Now this calculation, 75 times sine of 35, is not going to be negative. When you put it in your calculator, it's going to be a positive value. That's why we have to specifically look at which direction it's going, because we need to know which direction is it going to get that sign correct, positive or negative sign. So in this case, we get 43 again, but it's negative because it is going downwards. Okay. So all that stuff that we've looked at before, here's where we're going to put this together, because we want to look at is what happens when we put these together and add these two vectors together, because that's what we're going to be doing with the bridge trusses. Bridge trusses, we have a lot of forces acting, and we want to piece all that together and figure out the overall force acting on each of those bridge beams. So in this case, we have this boat. We're pulling with two ropes, and they're both pulling at a 35-degree angle from this horizontal. One's above it and one's below it, and they both the same force, both 75 pounds. And we've done this problem. If you looking back, these are the exact two vectors we just worked through. So when we do that, the way we want to work this out is we want to look at the x and y components, because we want to be able to add these together, and they're pointing different directions. And since they're pointing different directions, we can't add them directly. Now we could geometrically add them together, and the way you would do that is you take one vector, take the end of one vector and put it at the head of the other vector, and then get a resultant vector is kind of like the end of where the two vectors would end. So it's almost like doing a map. If I went this far in this direction and then I went this far in this direction, where would I end up? And of course, if I took that one and B and moved it up to the end of A and went out there, I'd end up out here somewhere. And you could definitely do it that way. But again, if we're going to do it algebraically, we need some other way of doing it. And that's why we break everything down to x and y components. Because once we get everything pointing in the same directions, we can add them together, or we could subtract them as necessary. All right, so let's take a look at that. We've already found all these vectors, so we don't need to find them again. So here's a quick reminder of what those were. So to do the resultant force, like the overall force of these two together, we're just going to add the x's together. And so we're going to add these two, FAX and FBX, and we're going to add our y values together, because these are going in the same direction. These are going vertically, while they're not pointing in the same direction as far as one's up and one's down, but they're both going along the same axis. So anything going in the y direction, positive or negative, is going to get added together. Anything going in the x direction is going to get added together. So we're going to add the two x's together, add the two y's together, and that is going to give us the x and y components of our resultant force, the overall force acting on this object. So this one's a pretty nice one. They gave us some good numbers for the y, because these are going to actually cancel out. So if we add these two together, we end up with 122.8 or 120.9 if you add in the extra decimal places that they rounded off earlier. That is our x component of our resultant force. Okay, so that means there's 122.9 pounds pushing us to the right with this thing. And then we add together our y components. In this case, they add up to 0, because one is positive, one negative, and they're the same angle and the same force. So we know that they're going to cancel each other, which means we have no force acting in the y direction. So all the resultant force of those two is pushing directly to the right. There's nothing pulling us left or right at all. So our final magnitude here is 122.9. Now, normally what we want to do is we want to do Pythagorean theorem, because f of x and f of y are the two legs of my right triangle. However, in this case, f of y is 0, so there is no second leg. It's just the one force. So this is our resultant vector right here. It's 122.9. So we know it's going 122.9 pounds in the positive x direction, so to the right. And so it's 0 degrees, so it's right along the x-axis with 122.9 pounds. So that is our resultant vector. So this is kind of what we're going to be doing with the all of the stuff that we're doing with the bridge trusses. You're going to have a lot of these type of calculations where you're finding the x and y components, you're adding them together, and then once we're done, we're going to find the resultant force on our beam once we're done. So anyway, that's kind of where we're heading. So this is just a quick reminder, a quick practice of on how this works. All right. And so here's the resultant force is going to look like that if we want to draw out that resultant force. And that is going to be where we leave off today. So I will pick this up again in part 2. Thank you.